Assalamualaikum and good morning, everyone.
Waalaikumsalam, Doktor.
Okay, so today we will discuss question number 4 from tutorial on truss. Okay, so the plane truss shown in figure 1 is composed of members having a square 15 meter times 50 meter cross section and modulus of elasticity E equals 69 gigapascal. Okay, so all of the member has the same cross-sectional area and the same elasticity. So the difference between each of the beam of the element of the truss is the length. Okay, so question A, determine the local stiffness matrix. Question B, compute the nodal displacement in the global coordinate system. And then lastly, compute the axial stress in each element. Okay, so let's go back to this question and let's see how to answer this. Okay, so firstly, we jot down the cross-sectional area. A equals 15 times 15. So this should be 225. Double check, okay. Okay, so 225 millimeter square. And then yang modulus 69 gigapascal. So firstly, we need to determine the angle of each of the element in the truss. Okay, so we go to first element. So the height is 3 meter and the length is 4 meter. And so the length of the element is 5 meter using Pythagoras theorem. Okay, so this is node number 1 and this is node number 4. And then we can determine this angle. So using cosine. Okay, so theta 1 is 36.87. And then we go to element number 2. So this is 4 meter and node number 2 and node number 4. Okay, so we measure our angle from positive x direction. Hence, this angle is 0 degree, okay? And lastly, element number 3. So node number 3 and number 4. And the height is 3 meter. The length is 4 meter. So the length of the element is 5 meter using theorem Pythagoras. Okay, so the angle we need to measure is this. Okay, so measure from x direction and take the angle of the lower number node. Okay, so theta 3. So we know that this angle is similar to theta 1. And so this is also theta 1, similar. Okay, using triangle rules. So the theta 3 will be 360 minus 36.87. So it's 323.13. Okay, so after you determine all the angles, then you can make the table for sine and cosine. So element 1, element 2, and element 3. And first the length. Okay, so this is in meter. And then the angle. Then we find the cosine and sine. So cosine, sine, cosine squared, and cosine sine. Okay, so let's compute. This is should be 4/5 and 3/5. 16/25, 9/25, and 12/25. And then this one, the second one, 1 0 1 0 0. And then the last one, so this is 4/5, negative 3/5, 16/25, 9/25, 12/25. Okay, so if I calculate wrongly, please correct me, okay? Then we can assemble the local stiffness matrix for question A. So when the question asks for local stiffness matrix, meaning that you need to find the stiffness matrix for each element separately. Okay, you don't need to combine them because it's local. Local means for each member, for each element. Okay, so let's find the for element 1 first. Okay, so what I did last week is I find the value of K equals EA over L. Okay, so let's do the same thing. So K element 1 bar is EA over L. So A and E are the same, but the difference is the L. So E is 69 gigapascal multiplied by 225 millimeter squared. So you get and then divide by 5. So here you get 3.105 times 10 power of 12. Okay, so convert the length in millimeter to make sure that you use similar SI unit. Okay, so it's better to conserve the SI unit in millimeter because usually the displacement is very small in truss element. So your answer will be in kind of whole number if you use millimeter. So if you use millimeter, so we go back here and change to millimeter. And we can calculate again for the K bar. Okay, so we get 3.05 105. times 10 power of 9. Okay, so unit is okay, apa unit dia Newton meter kot, tak sure. And then after we find k bar, we find the k. So k of the stiffness matrix of element 1 equals k bar times the matrix of sine and cosine. So cosine squared. So we just substitute this value here. So 16, 12, 16, 12, negative 16, negative 12. Okay, so we factorize 25. So this is the element stiffness for beam element number 1. Then we repeat for element number 2. And the stiffness matrix. And then for element number 3, okay, so element number 3 has the same length with element number 1. So the k bar is the same. And the stiffness Okay, so you get this should answer question A. And now we go to question B. Compute the nodal displacement in the global coordinate system for the load shown. Okay, so we can assemble the displacement matrix first, or the displacement vector. So we should have 8 elements, 8 displacement. So if you look at the question, then node number 1, number 2, and number 3 are fixed. So the displacement at node 1, 2, and 3 are 0, except here at node number 4, we have displacement in both directions. So we can substitute the boundary conditions into the displacement matrix. Okay, so the displacement for node 1, node 2, node 3 are 0. And for node number 4, we have u for x and u for y. So we need to determine these two displacement. Then we can find the force. We can assemble the force vector. So we have all forces because for each of the node 1, 2, and 3, we have support, okay? A fully support, meaning that we have internal reaction force at the support 1, 2, and 3. So we have all forces components in all of the elements. I mean nodes. Okay, so F1x. So we can substitute for F4x and F4y from based on the question given. Okay, so the force on node number 4, it's 5 kilonewton with an angle 30 degree from the negative, making a clockwise, okay, clockwise angle from the positive x axis. So we can split this force into x direction and into y direction. So let's do that first. So we can split this force into 2 directions. So if we take the positive direction as f4x, so we get 5k cosine 30, and then the y, we get negative. So we take the direction downward as negative and the direction to the right as positive. So we get negative 5k sine 30. So let's find this first. So we get negative 5k, 5 over 2k. And top one, we get 5 square root 3 over 2k. So we can substitute the forces. Okay, so the question asks you to find the displacement at node number 4, because we have found the displacement at the other nodes. So we need to find u for x and u for y. So we can just construct the matrix for the last two rows. Okay, you can construct the global matrix, global stiffness matrix, or you can just construct the matrix of the last two rows. So to construct the last two rows, first we label the stiffness matrix. Where is the location of displacement 1 and displacement node number 4. Okay, the other node and node number 4. Okay, so here it's u1x, u1y, u4x, u4y. Okay, so similarly, this one. Okay, so to find the matrix for the last two rows, we just need the element for that intersect this. Okay, I mean that has the row and column for u4x and u4y only. Then you can add them up in a matrix. Okay, so force equals kd, and so let's arrange for k first. So k, (16 k bar over 25 plus 1 times k bar 2 over 25 plus 16 k bar 3 over 25. Okay, so please add one by one carefully. Okay, so you get 16 over 25 k bar 1 plus 1 over 25 k bar 2 plus 16 over 25 k bar 3. Okay, so I saw your answer in the quiz. Most of you didn't multiply with k bar. Simply add 16 plus 1 plus 16. So that's definitely incorrect. Okay, so you have the k bar, the multiplier for the matrix. So don't forget about that. Okay, so the reason I factor the k bar is because if I put it inside the matrix, it will be panjang. Okay, it will be too long. You have decimals inside. You can easily mess up with the matrix. So that's why I factorize it out. Okay, to make sure that your calculation is neat. Okay, cleaner than having decimals inside the matrix. Okay, so continue adding. Okay, so these two elements here cancel each other, so you get 0 here. And now we can find the displacement. Okay, don't forget the kilonewton. Okay, so you can calculate this. Okay, so after you calculate this, you can find the axial stress. So to find the axial stress, you use the strain first. Find the strain. So strain for each element equals 1 over L. Okay, ni dah tak malas lah. Malas nak kira. Okay, kira sendirilah nanti. Okay. And then the displacement. And then to find the stress, simply find stress equals E times the strain. Okay, any question before we proceed with the next chapter?
Doktor nak tanya yang tu.
Here,
Cos.
cosine. Mana?
Oh betul, saya salah. Okay, betul. Masih betul.
Okay, so for your test, just do the tutorial is enough. Okay, don't worry too much. But I do have a trivial question for you to think. Okay, so what happen if, let's say, in this question number 4, let's say you add one more element. Let's say you add one more element here. Tak keluar. So what happen if you add one more element here? Number 5, and this is element number 4. So what happen if you add this element at node number 4 here? What happened to the global stiffness matrix? And what happened to the local stiffness matrix for the other existing element? So can you think about that? And maybe fikirlah kenapa? What happened if you add this element, element number 4? What happened to the global matrix? And what happened to the local stiffness matrix? Okay, is it changing or is it remains the same? So fikirkan. Alright, so let's move on to the next lecture. Okay, so beam element. Okay, so if you have any question, just stop me. Okay, maybe I'm moving too fast or tak faham ke ataupun mengantuk ke, beritahu. Okay. Okay, so beam element. Okay, my name is not Dr. Sarwani. Okay. Okay, so beam equations. In this section, in this lecture, we will develop the stiffness matrix of a beam. Okay, so similar to truss, we can also have a beam element instead of truss. Okay, so the reason why we use finite element method, tu tak tahu kenapa. Okay, I think you have learned about beam element or about beam maybe in SOM, I don't know. So the beam element is considered to be straight, okay, only straight, and have a constant cross-sectional area. Okay, so it is a straight, and sometimes it is in this form, bentuk huruf I. Okay, the letter I. Okay, so we usually we have two supports at each end. I mean, each end has one support, and we apply a distributed load on the beam, and the beam will deflect it, okay, or membengkok. Okay, so here we want to determine the deflection in the beam. So we will derive the beam element stiffness matrix by using the principles of simple beam theory. And for beam element, the degree of freedom is not only the displacement, but it involves the rotation. Okay, so we have displacement and also the rotation of each node. So different with truss. So in truss we have displacement only, but we split the displacement into x direction and y direction. But for beam we have displacement and rotation, and we can also split the displacement into x and y direction. But I think in this lecture we only focus on the displacement in one direction only. And then we will discuss the procedure to derive the equation when there is a distributed load or concentrated load on the beam. And also we'll include nodal shear force. What happens if we have shear force in the beam and a bending moment in the beam? And we can develop the beam bending element equation. And lastly, we will use or derive the Galerkin residual method, which is applied for beam element. Okay, but maybe for this week, we only cover the first half only. Okay, so consider your beam element as shown here. So you have two nodes, node 1 and node 2. So in each node, we have phi. So phi 1. So the symbol phi represent the rotations, okay, rotation of the node. And M1 represent the bending moment of that node. And similar to node number 2, we have a bending moment M2 and rotation phi 2. And then we have the length of the beam L. And on each node, we have a force F, F1, F1y acting upward. Okay, so in this case, it's acting upward. So node number 2, also we have F2y. And we have the V here. So V is the displacement. So small v is the displacement of the node. Okay, so here we only consider the displacement in one direction, which is in y direction, because we assume that the beam only bending, okay, bended, and it doesn't move left to right or horizontally. So to analyze beam, we need some sign conventions before we can derive the equations. So we always assume moments are positive in counterclockwise direction. So counterclockwise moments are positive, similar to rotation. So counterclockwise rotations are positive, and forces are positive if it is acting upward or positive y direction. And similarly, for the displacement, also positive when y is positive or acting upwards. So the differential equation governing simple linear elastic beam behavior can be derived as in the following slide. Okay. So firstly, we assume that we take a small element in the beam. Okay. Maybe the length is AB or CD. We take a very small element inside the beam, and from there we derive the beam stiffness equation. So this is the small element that we take, and then inside the element we have V, big V here represent the shear force. So V, big V is the shear force at each node on the small element. And then we have M, and then the other side is M plus a small change of m, okay, dm. And then the length of the element, of the small element, is dx. Okay, so it's like deriving using differentiation, okay. So we take a small element and whatever. So we derive the moment. And then we assume that dx squared is very, very, very small. So we can cancel out the dx squared terms. So what happened is that we get the shear force V equals dm over dx, or the differentiation of the moment with respect to x. So we get the shear force. And then the W is the distributed load. Okay, so W here, behind the green arrow here, it's the distributed load applied on the beam, on the small element of the beam. So the distributed load W equals the negative of differentiation with respect to x of the shear force. Okay, so we can substitute V with dm over dx. So the distributed load W equals negative d dx of dm dx. Okay, so I think these three formulas are important. V equals dm dx, W negative dv dx. Okay, so these two formulas are important. Need just substitute. And then the curvature kappa of the beam is related to the moment. Okay, so ni dia tak derive, dia bagi je. So take as it is. Kappa equals 1 over rho. So rho is the radius of the deflected curve. So it's equal m over E times I. I is the moment of inertia. And then the curvature for small slopes is given by kappa equals d squared v over dx squared. Okay, so here phi is the rotation that I said previously. So rotation is equals dv over dx. Okay, so this v, I think it's the displacement, okay, not shear force. Okay, so you end up with this equation at the end, ei times d4v over dx4 equals negative w. Okay, so we have a lot of equations that we need to jot down, okay? So first is this V, shear force, and then the distributed force, and then this one, the last one here, the relationship between distributed force and the displacement. And we have the rotation here, also important. Semua pun penting, okay? Tapi the one that I said the most important will be used quite a lot. Okay, now let's derive the stiffness of a beam. Okay, so let's say we consider a linear elastic beam shown below, shown here. So this is similar to the first figure that I showed just now. This one. So we now want to derive the beam stiffness. So remember, counterclockwise rotation or moment are positive, and force acting upward and displacement upward are positive. Okay, so in beam, so we have the transverse displacement or the displacement V. We can derive it in terms of x using this equation. Okay, so we call this displacement function. So in finite element method, we have a lot of displacement function, but the most common one, we use a quadratic or not quadratic polynomial equation or polynomial function. So we express v in terms of x, or the x is the location of the beam length. Okay, it's this x direction. We can use a polynomial equation or polynomial function. So v equals a1x cubed plus a2x squared plus a3x plus a4. So a1, a2, a3, and a4 are just coefficients of this polynomial. So we want to determine this a1, a2, a3, and a4. The number of coefficients in the displacement function is equal to the total of a number of degree of freedom. So we have displacement and also rotation as the degree of freedom. So in the beam just now, we have two degree of freedom at node number 1, which is the displacement v1 and the rotation phi1, and also 2 degree of freedom at node number 2, v2 and phi2. So we have 4 degree of freedom here. So that's why we use 4 coefficients polynomial or third order polynomial. So firstly, we substitute the boundary conditions. So at x equals 0, we assume that the displacement as v1. Okay, we go back here in this figure. So at node number 1, or at x equals 0, displacement is v1. And at x equals L, the displacement is v2. So this is the boundary condition. And also we can substitute the boundary condition for the rotation or the phi. So phi, it's dv over dx. So at x equals 0, it's phi 1. At x equal L, it's phi 2. Then we can apply the boundary condition into the displacement function, this displacement function. Okay, so we substitute at x equals 0, v equals v1. At x equals L, this v equals whatever. So here we substitute. So v0 equals v1 equals a4. So we find our a4, and v2 we get this equation after we substitute x equals L. And then we repeat for dv over dx. So first we differentiate dv over dx. So we differentiate this dv over dx, and then substitute x equals 0. So we get phi 1 equals a3. So we get our a3. And then differentiate dv over dx. We substitute with L, x equals L. So we get phi 2 equals this. So now we substitute a4 equals v1 and a3 equals phi 1 in these two equations here to find a1 and a2. So our motive now is to find all the coefficients, a1, a2, a3, and a4. So now we have a4 and a3. We need to find a1 and a2. So substitute a4 and a3 and solve these two simultaneously. So entah macam mana dia solve, dia dapat ni. Nak try sendiri, jangan tanya saya macam mana dia buat. Try sendiri. Okay, so we can express our displacement in terms of matrix. Okay, we can do this similar to F equals K times D. But now we express the displacement equals N times D. So D is the degree of freedom. So this is our V. So we can express it in N times D. So we get the D, V1, phi1, V2, phi2. So these are our degree of freedom, the uh, the variables that we want to find, and N is something, okay, N1, N2, N3, and N4, which are given here, okay. So these are our N's, N1, N2, N3, and N4. Okay, so now the displacement can be found easily by substituting the location X that we want on the beam. Okay, so and all of the N's are called the interpolation functions. Okay, so it interpolates along the beam because it depends on the X. Okay, so this is an example of the N, all of the N's when you plot this graph. Okay. And now we want to find the, we continue by finding the stress strain, stress displacement relationship. Okay, so the strain equals du over dx. Okay, so we can relate the axial displacement to the transverse displacement by considering the beam element. Okay, so and again we take a beam element, a small beam element, and then we find using the similar things that I've explained previously. So I think the derivation didn't show here. So u equals negative y dv dx. So y here is the height, okay? Height of the beam. So the strain equals du over dx equals negative y d squared v over dx squared. And then we can find the moment and shear force. Okay, using again using the formula that I explained previously. So moment equals ei d squared v over dx squared, and the shear force v equals ei d cube v over dx cube. Okay, so many formula. Mana stiffness matrix tak sampai. Okay, so again we can derive the shear force and bending moment. And then using beam theory and sign convention that I explained previously, we can find the shear force F1y. So shear force of each of the nodes and also the moment of each of the nodes. So we just differentiate, okay? So we got our V and we just differentiate the V. So we get this for forces and also moment. And then we can substitute this into the well-known matrix form, F equals K times D, okay? Or we can simply form this in equation and arrange them in matrix. So we got this matrix here. So what we want to find now is the displacement or the degree of freedom, displacement and rotation given your force and moment. Okay. So the middle matrix here, the EI over L cube and the 4x4 matrix are your stiffness matrix. Okay. So this is the stiffness matrix for a beam element K equals EI over L cube and this 4x4 matrix. Okay, so this stiffness matrix kenalah tulis dalam toyol. And then let's look at an example how we can use the concept of stiffness matrix to find the degree of freedom in a beam. Okay, so let's look at one example. So consider a beam modeled by two beam elements. Okay, so this is a single beam, but we have a force in between. Okay, a downward force and a moment. So we want to find the displacement and rotation at each node, node number 1 and node number 3. So it's easier if we can split this beam into two beams. Okay, macam pelik kan, kenapa nak split? That's how we can use finite element method. So a single beam, we split the beam into two beams. Okay, so we have the first element here, which consists of node 1 and node number 2, and element number 2 here, which has node 2 and node number 3. So at node 1, it is a fixed support, and node number 3 also a fixed support. Okay, so assume that the EI to be constant throughout the beam. So EI is constant, and the force of 1,000 pound applied downward, and a moment of 1,000 pound feet. Kenapalah guna USA convention ni? Are applied to the midpoint of the beam. Okay, so first we find the stiffness matrix of the element number 1. Okay, so we just use the stiffness matrix equation for the beam. Okay, so jangan tanya kenapa 12, 6 tadi dalam slide sebelumnya. So we just label each of the row and column represent what. Okay, so here it represent V1, phi1, V2, phi2. Okay, and then we find the stiffness matrix for the second beam. So similarly, we label the column V2, phi2, V3, and phi3. So the purpose of this label is to make sure that you don't confuse what this column represent and what this row represent. Okay, so the stiffness matrix are the same because EI and the length are the same. So if the EI and the length are different, so your EI over L cube will be different. Okay, so again, make sure that you take note of this EI over L because it is factorized outside. Okay, so similar to truss element just now, it is factorized. So when you add the stiffness matrix later to find the global stiffness matrix, so don't forget to multiply with this EI over L cube. But in this case, it's similar, so you can always factorize it later. But for cases that this EI over L cube are different, make sure you multiply first before adding. Okay, so you can form the global stiffness matrix and subsequently form the global equation. Okay, so you just add up the matrix. Okay, so I hope by now you know how to add this matrix up. Okay, but if you don't know, you can do the truss element tutorial to get an idea how you can form this matrix. Okay, and then after you form this matrix, similar to truss element, you substitute the boundary conditions for the displacement and rotation. Okay, so in this case, if we look back at the figure, at node 1 here, the displacement is 0. At node number 3, the displacement also 0. Okay, so we get 0 displacement at node 1 and node 3. And then at node number 1, because it's a fixed support, the rotation also 0. But at node 3, I'm not sure why. I forgot what support is this. I think this is a pin support. So a pin support, you can the node can be rotated. Okay, so you have rotation at node number 3, but at node number 1, it is fixed. It cannot move. Okay, But note number 3, it's a pin support, so it can rotate, but it cannot displace. Okay. So maybe it's worth if you can go back to lecture on statics to see what this support, what are the nodes or what are the degree of freedoms given by each of the supports. Okay. So we substitute these boundary conditions into the displacement matrix. Then we can find the remaining displacement and rotation. So we apply the force, the load boundary condition, and so we our matrix are reduced to 3 by 3, and then find V2, phi2, and phi3. Okay, so you get this V2, phi2, and phi3. And then we can continue by finding the element strains and stress. So to find element strain and stress, first we need to find the moment and shear force. And then we can use the formula for strain. Mana tadi? This one, okay, for strains. Okay, any question before we end our lecture? We continue next week on looking at more examples, okay?
Doktor, slide ni dah ada dekat kalam?
Saya baru upload tadi.
Okay, masih Doktor.
Okay, so as usual, as requested by Fadli Nadil, I want to give you a quiz, okay? Which is the due date is next week. So this quiz is simple je. I want you to rederive the equation for the beam just now. But now we change the sign convention. So I want you to derive this equation starting from this slide. But in this slide, we assume that the rotation is positive counterclockwise. So what happens if we assume now the rotation is positive clockwise instead? So rederive the element stiffness matrix of the beam element, assuming the rotational degree of freedom, or the phi, is positive in clockwise direction instead of counterclockwise. Okay, so you rederive and then compare your new stiffness matrix with the one that is derived in the lecture notes. Okay, so the lecture notes, the stiffness matrix is given as this. Okay, so what happens if your phi is now in positive clockwise direction? Is this stiffness matrix change? So try to rederive and then compare your answer with the one in slides. Okay, so the due date for this macam last week so due date is 21st 11:59 p.m. 21st December. Okay, so try to rederive and then compare with the one in slides. Okay. Okay, any question before we end this lecture?
No, Doktor.
Okay. Thank you very much and see you again next week. Inshallah. Assalamualaikum and goodbye.
Thank you, Doctor.
Salam, terima kasih Doktor.
Thank you.
Salam, thank you Doktor.
Okay, Doktor.